deals with some more with our trig ratios. This time we're going to not necessarily work within the unit circle. We're still going to have our initial side, terminal side, standard position, angle, but this time we're going to not know the angle, but we're going to know a point on the terminal side. And this is still going to be enough information for us to generate all 6 ratios. And then we're also going to do a couple of problems asking about in which quadrants would satisfy particular characteristics, and then an application problem. Take a moment to pause the video and review the vocabulary, the I can statement, and the why for today's lesson. And after you've done that, then you can resume play. So our first example, we need to determine all 6 trig ratios for an angle whose terminal side contains the point -3, -4. So we start with our coordinate plane. And we know this is always going to be our initial side. And now we're going to rotate all the way to quadrant 3, right? Because both the x and the y will be negative. And then we'd have our coordinates for this point, -3, -4. Now we're going to use our reference angle. We'll drop our perpendicular. And now maybe let's do some labeling. Here we have our x coordinate, -3, our y coordinate, -4, and this is our angle. But we're using this reference angle to write our ratios. So we have the sine of theta, the cosine of theta, the tangent of theta, and then we would have the cosecant of theta, the secant of theta, and the cotangent of theta. Remember, these are reciprocal functions. So the cosecant of theta is really 1 over the sine of theta. So we just flip the ratio. Oops. I'll set up our ratio. I think I would even get the signs now. Remember, all students take calculus. So in our third quadrant here, only the tangent is positive, which means the sine ratio and the cosine ratio are negative. The cosecant and secant ratios are negative. Only the tangent and cotangent would be positive. And then we need to get our hypotenuse for our sine, cosine, cosecant, and secant ratios. You can use Pythagorean theorem. Here, this radius is not necessarily equal to 1 because this is not, we're not talking about the unit circle. So you would say 3 squared plus 4 squared would give me our hypotenuse squared. Or if we were using the circle analogy here, the radius squared. Or you could remember that this is a 3, 4, 5. That's a Pythagorean triple. And then that radius is always going to be positive. But you can see this will play out. Square root of 25 is 5. So now we fill that in. Denominator, denominator, numerator, numerator. The side opposite is 4. The side adjacent is 3. Then the tangent would be opposite over adjacent. Then we put our 4, our 3, adjacent over opposite. Okay, number 2, we want to determine the remaining trig ratios given 2 of the ratios. So the first thing we want to examine is the sign, SIGN, of both ratios. So the cosine here is positive, which means we're talking about an angle that maps into either quadrant 1 or quadrant 4. For all students take calculus. Cosine and everybody in quadrant 1 or quadrant 4. However, the next piece of information says the tangent ratio for that same angle is negative. Well, tangent is negative in quadrant 2 and 4. Because only the sine is positive here and only the cosine is positive here. 2 and 4. And we can see the agreement, or the quadrant in which both conditions are satisfied, is quadrant 4. So now we sketch an angle that maps into quadrant 4. Initial side is always our positive x-axis. Here's our terminal side. And we'll draw our triangle with our reference angle here. Now, using the ratios, let's just write them out. So we need sine. We already have the cosine ratio, which is 12 over 13. So this is adjacent over hypotenuse. So here's 12 and here's 13. And then we have our tangent ratio of negative 5 over 12. So the side opposite is our negative 5. And here's our reference angle. So now we can get our sine ratio. That's going to be our opposite over our hypotenuse. And then we can get our cosecant, our secant, and our cotangent. Notice I am writing every single component of the ratio. I am writing the function, sine or cosine or tangent or cosecant or secant or cotangent. I am writing the angle that comes next, the theta. Then we have the equals. And then finally you have the ratio. Okay, our next example is going to be like we started the previous one. We want to know in what quadrant or quadrants would the terminal side of an angle theta lie in to satisfy the given condition. So cosine is negative in either quadrants 2 or quadrants 3. Again, sketch for yourself. All students take calculus. Negative here and here. Secant. Okay, secant is related. You might want to write off to the side here. Secant theta is just 1 over the cosine of theta. So again, we're talking about the cosine being negative here. And that happens. We've already got that answer from the previous problem. Quadrant 2 or quadrant 3. That's where our cosine is negative. This is from the previous problem here. But sine function needs to be positive. sine is positive in quadrants 1 and 2. And then the only match that we have here is quadrant 2. So an angle that would terminate in quadrant 2 would satisfy both conditions. Now we're asking the same question, but in a little different way. We are going to figure out the quadrants just like we did in the previous example here. But then we're going to amp it up and give the theta some parameters. And we're going to give it an interval for the angle in degrees and an interval for angle values in radians. And I think I'll write it both as an inequality and as an interval, just so we just practice both notations. So sine of theta is positive, while tangent of theta is negative. So sine of theta positive, quadrants 1, quadrant 2. Tangent negative would be quadrant 2, quadrant 4. The match here is quadrant 2. And so to lie in quadrant 2, theta would have to have rotated more than 90 degrees, but less than 180. If we put that in terms of radians, we have the interval from pi over 2 to pi. Here, cosecant, which is 1 over the sine of theta, is negative. So sine is negative in quadrant 3 and in quadrant 4. Cotangent, which is 1 over the tangent of theta, is also negative. Tangent is negative in quadrant 2 and quadrant 4. We see the quadrant 4 is the match here. So for an angle to terminate in quadrant 4, we would rotate at least 270 degrees, but less than 360. Write that in an interval notation. Convert that to radians. This would be 1.5 or 3/2 pi less than 2 pi. And our last type of example here, we're going to use radians to find arc length. So we have a satellite that's being tracked, and it's traveling in a circular path above the Earth. It can only be tracked while it orbits through a pi over 6 angle. The radius of the Earth is 6,400 kilometers. What is the distance the satellite travels while it's being tracked? So let's sketch. So the first circle here is going to represent the Earth. And here is our 6,400 kilometers of the radius. Then we have the satellite being 320 kilometers above the Earth's surface. So we could make another circle. So we have these two concentric circles, and this is the center of our Earth. And then as it travels this path, we're only able to track it in this window here of a pi over 6 angle. And we're going to use our arc length. This is what we need to find. And here we have radians. So remember our formula was our angle measure is arc length over the length of the radius. So pi over 6 is equal to S, that's what we're solving for, over the radius. And the radius here of the satellite's path is 6,400 plus 320 kilometers. So that's 6,720 kilometers. And then we're going to solve for S. And you could multiply each side by the reciprocal. You could use the cross product property of proportions. So I'd have 6 times S is 6,720 kilometers times pi. Sorry. So then we would solve for S by dividing both sides by 6. And then now that we have our expression, now we get our calculator. And we take 6,720 times pi and divide by 6. And we get 3,518.6 kilometers. The satellite travels 3,518.6 kilometers.